To start, I'm going to let y of 1 just be the set of isomorphism classes of elliptic curves over the complex numbers. So when we say moduli of elliptic curves, we want to think about this set of things and maybe put on some structure on this set, give it the structure of a manifold or a variety or something of that sort. And we'll do that in a second, but I think it's good to have some other examples in mind because often you don't care just about just this thing, but a few related sets of things, the curves of extra data. So I want to introduce those so you can have them in your head as examples as we go on. So there's three that are kind of the most common, most important. So the next one is called y1n. So here n is a positive integer. And this is the set of isomorphism classes of pairs E comma P, where E is an elliptic curve, and P is a point of exact order n. And by an isomorphism, so an isomorphism from EP to E prime P prime is an isomorphism of curves E to E prime, which takes P to P prime. And then there's y0n. This is the set of isomorphism classes with pairs E comma G, where again E is an elliptic curve. And here G is supposed to be a cyclic subgroup of G of order n. And finally, there's y of n with no subscript. And this is the set of isomorphism classes of pairs E comma, and then, well, maybe I'll just call it triples, E comma PQ, where again E is an elliptic curve, and P comma Q is the basis of the n torsion. So when I say we want to think about moduli of elliptic curves with some extra data, these are kind of the examples to have in mind. Just carry around a torsion point or a subgroup or some variant or something like that. And then there's some relationships between these particular moduli problems, or sets, I should say. Y of n maps down to y of 1. This maps down to y of 0. And this maps down to y of 1. And these maps, well, here, this map, you just forget Q. Right, here I have a basis PQ, here I just want to P, so I just forget Q. Here I take the subgroup generated by P. And here I just forget the subgroup. All right, so the goal for today is to kind of describe these things in a nice way, give them the structure of a complex variety, and try to understand a little of the geometry of those varieties. Are there any questions? All right, so let's start by thinking about just y1. So we already know a description of this set. Can anyone tell me? Anyone tell me audibly? Yeah. So the J invariant, assigns to any elliptic curve a complex number. It's well defined in isomorphism classes, and we know that over an algebraically closed field, the curve is determined by its J invariant, and every number can occur as a J invariant. So this J invariant is a bijection. So that gives kind of a complete description of this set. It's C. And using that, you can give this thing a structure of a complex variety if you want, right? Because this is a complex variety, you can just move it back. So y1 looks like a1. That affine line is a complex variety. That's a perfectly good description, but this kind of thing is not going to generalize so well going to y0n or y1n. So we want a different way to describe this. And the kind of key way to do it is through lattices. So we're gonna come up with a different way of getting at y1 by thinking about elliptic curves in terms of lattices. So we know that every elliptic curve E can be written as, so every elliptic curve E is of the form C mod lambda, or lambda some lattice. And you know that if you take a lattice and you scale it by some non-zero complex number, the elliptic curve it defines, the quotient, is the same as the original one, the isomorphism. So we can replace lambda by a scale. Say alpha times lambda. And so we may as well assume that 1 is a generator of lambda. So I'll write that as lambda equals 1 comma z. So by this I mean the subgroup of C generated by 1 and the number z. And of course, to get a lattice, z can't be in the real numbers, otherwise we'd get some weird rank 2 subgroup of R. So here z is not a real number. And if you think of C minus R, right, there's two pieces. There's the upper half plane and the lower half plane. And of course, you could replace z by negative z. So you may as well actually assume that z is in the upper half plane. And I'll denote the upper half plane by h. So maybe I'll write that. So h here is the upper half plane, so this is the set of complex numbers whose imaginary part is strictly positive. And to just kind of say more clearly what I said here, for z and h, let lambda sub z be the lattice generated by 1 and z. So this is the lattice in C, and I'll let E of z be the quotient. So this defines a map just of sets from the upper half plane to y of 1. We can take the point z for the elliptic curve E of z, and we know that this is surjective. That's what this simple reasoning showed us. It's not injective, right? Different points in the upper half plane can generate lattices that have isomorphic quotients. And here's how you can see that. So suppose, okay, not injective. So suppose that, we have some lattice 1z. So this has a basis. So, okay, so if A, B, C, D is an element of SL2z, then of course I can take these two basis vectors and replace them by linear combinations like this, and I'll still have a basis. So AZ plus B and CZ plus D also form a basis. And so now if I scale by CZ plus D inverse, this says that AZ plus B over CZ plus D and 1 form a basis for CZ plus D inverse times lambda z. And of course, the lattice that this thing makes is just by definition lambda of this thing here, AZ plus B over CZ plus D. So this shows that this lattice and this lattice have isomorphic quotients. And so the point Z and the point AZ plus B over CZ plus D are in the same fiber of this map. Okay, so let me state this more carefully. So I'm going to let gamma 1 just be alternate notation for SL2Z. And for an element here, A, B, C, D, and so for gamma in there and Z in the upper half plane, gamma of Z is defined as I wrote over there, AZ plus B over CZ plus D. And you can check that this formula defines an action of gamma on the upper half plane. So in other words, if I have a gamma and a gamma prime, and I compose these operations, these are called linear fractional transformations, then the resulting linear fractional transformation is the one corresponding to the product matrix, gamma and gamma prime. And so what we just showed over there was that gamma Z and Z lie in the same fiber, so that means that we get a map in the quotient, the upper half plane mod gamma 1 to y of 1. And what I want to say is that this is a bijection. So in other words, these kind of obvious identifications of Z with its orbit under gamma are the only ones that occur. And so here's a proof of this. So we just need to show the kind of injectivity part, because we already know surjectivity. So suppose EZ is isomorphic to EZ prime, which is the same thing as saying that lambda Z is some scalar multiple of lambda Z prime. Okay, so 1 lives in this lattice lambda Z, so that means that 1 lives on this right side. So that means I can write 1 is alpha times CZ plus D, CZ prime plus D, for some integers C and Z, C and D. So these integers have to be coprime. Because if E divided both of them, then dividing this expression by E, you'd get 1 over E is alpha times C over E, Z prime plus C over E. And this thing on the inside, since C over E and D over E are integers, lives in lambda Z prime, right? And so this thing lives in alpha times lambda Z prime, which is lambda Z. And so that would tell you that 1 over E lives in lambda Z. But that doesn't happen. It only happens if E equals 1. Okay, so that proves that they're coprime. So we can pick A and B such that AD minus BC equals 1. Right, that's a basic fact about coprime integers. In other words, we can find an element of SL2Z whose bottom row is C and D. And so this alpha lambda Z prime is the same thing as lambda of gamma Z prime. And so this shows that this lattice lambda sub gamma Z prime is equal to lambda of gamma Z. Or sorry, lambda sub Z. And that doesn't actually imply that Z is equal to gamma of Z prime, but it almost does. So if you think about what this says that we can write Z as, say, n gamma of Z prime plus m, and we can write Z prime as, say, n prime Z plus m prime. And so if you combine these two expressions, you see that Z is equal to n mz plus some integer. And now if you look at the imaginary parts of these expressions, you find that nm has to equal 1. And so let's just pretend that n and n are both 1 instead of maybe minus 1. So that says that, z is equal to gamma of z prime plus some integer n, and this is actually just equal to gamma prime of gamma of z, where gamma prime is the matrix 1, n, 1. Okay, so the gamma that we picked may not have been right, but if we fix it by this gamma prime, then we get the right thing. Okay, so this is our, the J invariant gave us one description of y1. This is a different description. It's realizing it as this quotient of the upper half plane. Yeah. Yeah, I think if you just look at if you pick an isomorphism, it has to induce some half-on lattices, right?
Yeah.
And from the description in terms of exponentials, it has to be an isomorphism of lattices.
Yeah. Okay. I'm just curious.
Right, so we have these two descriptions now. Y1 is the upper half plane on gamma 1, and it's also C. When I want to say maybe two comments about the fact that these two things are equal. I don't think it's obvious if you started from scratch. So first of all, the J invariant, the J invariant is the function from y1 to c, so you can think of it as a function on h which is invariant by gamma 1. So in other words, there's this function which takes z to the J invariant of this elliptic curve EZ. And if you go through, how E of Z is constructed, it's this quotient, but it has some Weierstrass equation, and the coefficients are given by some analytic function that's fairly explicit in Z. This comes from the analytic theory of elliptic curves, and the J invariant is given by a similar expression. So if you go through that, you can see that this function here is actually a holomorphic function. So this is a holomorphic function on the upper half plane, which is invariant by gamma 1. It's kind of weird. If you didn't know the theory of elliptic curves, it'd be hard to construct such a function. So if you don't believe that, I think you should try. Okay, so you get this kind of interesting function from this picture. So even without thinking about that function, though, and all this elliptic curve theory, you can see that this quotient is a genus 0 curve with a point missing by using fundamental domains. So it's this very famous picture that you should know about. So gamma 1 is generated by two elements. So 1, 1, 1, and minus 1, 1. And these correspond to the linear fractional transformations z goes to z plus 1, and z goes to minus 1 over z. And so if I have anything in the upper half plane, so let's think about the upper half plane like this. So here's the imaginary line, here's the real axis. Using this thing, z goes to minus 1 over z, you can move it outside of the unit circle. Right? If you have something in here and you apply that, it'll move it out here somewhere. And using this transformation, you can always move it so that the real part is between minus a half and a half. So this here is the point I, and this here is the 6th root of unity rho. This is e to the 2 pi I over 6. So you can move, say your point here, you can move it into here, and then maybe it comes back out here, and then move it back in. And anyway, the point is that you can show that you can move any point into this region here. This whole thing. And it's unique, except some points in the boundary. So that's why this thing is called a fundamental domain. And so if you think about what's identified, this boundary line here is identified with this boundary line, right? Z goes to z plus 1, takes those two things to each other. And this thing here is identified with that thing here, by z goes to minus 1 over z. And so if you think about making these boundary identifications, this gets glued to here, and you get a cylinder, and then you kind of sew up the base. And so that gives you just a sphere with this point at infinity missing. So that's a kind of a topological way that you can see that this quotient is basically Q1 with the points. So this description here of y1 in terms of this quotient generalizes very nicely to these other moduli things that we had, like y1 and y0. So let me just tell you one of them. So we can, if we have a point in the upper half plane, we can produce an element of y1n. So remember, y1n was the elliptic curve with a point of order n. And we just take z to the curve ez, so that's our curve, and now we have to give a point of order n. And what we do is we take just the point 1 over n, by which I really mean its image in E of z. So this Ez here is C mod 1 comma z, and the number 1 over n here, it gives you an n torsion point of Ez, because when you multiply it by n, you get 1, which is in the lattice. So this, it's easy to see that this is a surjection. Every elliptic curve with a point can be realized in this form. And again, it's not an injection. There are some identifications. But there are fewer than before, because you have to preserve the point instead of just the curve. So if you think about where gamma z goes, well, let me think about the lattices instead. So you have lambda sub gamma z on 1 over n. And now if I scale this, if I multiply by cz plus d, this comes back to lambda z, and here I get cz plus d over n. If I just multiply through by cz plus d. And this point here, and so now I have the same elliptic curve as if I didn't put a gamma, but possibly a different point. But this will be the same point if c is divisible by n, because then this is going to give you a z plus something, and that z is in the lattice, so it goes away. And if d is 1 mod n, right? So this is the same point. So that means we should consider the matrices which satisfy those conditions. So that's called gamma 1. So gamma 1 of n is the set of integer matrices such that gamma is, so you have a 0 and a 1 down here, mod n. And of course, since we're in SL2, that means that it has to have that form. So it really reduces to that mod n. And so that argument that I was saying over there says that the map from H to Y1 I constructed actually induces a map from the quotient by gamma 1n to Y1n. And this is an isomorphism. And then there's a similar result for Y0 and Y. So let me just say what they are. So if you put gamma 0 of n to be the set of gammas which are of the form just upper triangular mod n, but no longer with ones in the diagonal, then you get that this quotient is y0n. And for y of n, the group is called just gamma of n. And it's the set of things that just reduce to the identity mod n. Okay, so all these kinds of sets that we have of elliptic curves with some little extra torsion data can be described as quotients of the upper half plane by subgroups of SL2Z. These are all finite index subgroups of SL2Z. Are there any questions about this? Okay, so now I want to talk about kind of how these things are geometric objects. So now that we've seen some examples, I'm just going to work with an arbitrary finite index subgroup. And I'm going to define y gamma to be the quotient. And I'll let pi be the quotient map. Okay, so everything that we've just been talking about fits into this setup. So you can show generally that, I mean, when you have a finite index subgroup, that this quotient as a topological space is nice enough. It's not some horrible thing. It's a Hausdorff space. It's a nice topological manifold. I'm not going to go into the details there. If you want to see all the details of this, you should look, I mean, a good place to look is Shimura's book on automorphic forms. So you can give this thing a complex structure by as follows. So we declare a function from on y gamma to c to be holomorphic. If its pullback is. And you have to check this, but it's true that this turns y gamma into a complex manifold, in fact, a Riemann surface. So the problem that I was talking about is that, I mean, if gamma has torsion, then the action of gamma on the upper half plane is not, it has fixed points then. And so when you're doing a quotient that has fixed points, it's not as nice. It's not going to be like a local homeomorphism. We'll see that in a little while. It screws up the local behavior. But I think this is the right, I think I have the definition right of the manifold structure. Okay, but before I talk about that, I want to talk about how to compactify these things. So y gamma is never compact for these gamma. We already saw that y1 was just c. It's missing a point at infinity. And so there's a nice way to systematically compactify all these things. So you define this h star to be the upper half plane together with the q points of P1. So that looks a little weird. One way to picture this is if you think of the Riemann sphere. This is P1C. Then this equator here, that's P1R. And so when you remove the equator, you get these two pieces. And the top one is the upper half plane. And then we're just taking the points in this equator that are actually rational and adding them in. So it looks quite strange. So we're going to regard this thing as a topological space, but it's not quite the subspace topology. So the open sets, so these points here are called cusps. And here's what the topology is at one of these points. So a neighborhood basis at a cusp it consists of the disks in the upper half plane that are tangent to the equator at this point, things like that. So I mean open disks, but I mean with the point x included as well. So to be more precise and not kind of use this picture, a neighborhood basis of infinity is given by sets that I'll call UK, just the set of things whose imaginary part is greater than k, together with infinity. So if you think in the upper half plane, infinity is way up here, and we're just looking at sets like this. And as you move the line up higher and higher, you get smaller and smaller open neighborhoods of infinity. The group gamma 1, we know it acts on H. Of course, it also acts on P1. And the action on P1 is transitive. And so often that means that you can just define things up to cusp at infinity, because you can just move all your definitions around by gamma 1. And that's what we do here. So a neighborhood basis of gamma times infinity is just gamma times UK. Just gamma and gamma 1. And so this defines the topology everywhere because the action is transitive. Okay, and so then we make a definition. X gamma is this H star mod gamma. And I'm going to give it a complex structure in the same way. Function's holomorphic if its pullback is. And then it's a fact that this is a compact Riemann surface. So the only points that y gamma is missing are these points that are coming from QP1. There's finitely many of them on X gamma. That's true because since gamma 1 acts transitively on P1Q, and gamma has finite index in gamma 1, it's going to act with finitely many orbits on P1Q. And so those finitely many points on this curve are also called the cusps. Both upstairs and downstairs are called the cusps. So there's finitely many cusps that you add to get something compact. So y gamma sits inside there as the non-cuspal points, and well, at least in the case of gamma 0n and gamma 1n, we know what those points mean moduli theoretically, elliptic curves with some extra data. And so you should try to think about what the extra points mean moduli theoretically, these cusps that we've added. I'm going to talk about that soon, but it's good to try to think about that on your own first. All right, so we're going to try to understand the geometry of these Riemann surfaces a little. I want to compute their genus in particular. That's what I'm going to work towards today. And so to do that, well, you need to understand some finer properties of this quotient. And I said, the problems come in at the points where there's stabilizers and the action's not free. So I want to understand what do the stabilizers of the action look like. Stabilizers. We'll start with gamma 1 on the upper half plane, H star. Okay, so precisely what I mean, I'm going to let gamma 1 sub z, this is the stabilizer, so I mean a set of elements in gamma 1, which just fix z. So that's a definition. And note that this always contains minus 1. So by minus 1, I mean the matrix minus 1, minus 1. And the linear fractional transformation this defines is z goes to minus 1 z plus 0 over 0 z plus minus 1, which is just z. So this is a non-trivial element of SL2z, but it always induces the trivial map on the upper half plane. So it stabilizes everything. So sometimes we don't want to worry about that, so we'll look at the quotient group. So gamma 1 bar, I'm going to define to be gamma 1 mod plus or minus 1. So this thing acts faithfully on that upper half plane. Nothing in here is acting trivially. Okay, so the first observation about stabilizers is that there's a nice interpretation of them in terms of moduli. So the stabilizer in the full gamma 1, not this gamma 1 bar, is identified with the automorphism group of the corresponding elliptic curve. And let me explain how that works. So suppose that we have some gamma that stabilizes Z. And let me write it as ABCD. Okay, so this is an element of SL2Z, so it gives you an automorphism of the lattice Z squared. And so it gives us an automorphism over the lattice lambda Z. So I'm going to call that automorphism G. So precisely, so this lattice lambda sub Z is a lattice with basis 1Z, and this G is going to be the thing with matrix this with respect to that basis, or maybe I have it flipped. So precisely what I mean is that GZ is AZ plus B, and G of 1 is CZ plus D. Okay, so that's a Z linear map of this free Z module. So the condition that gamma Z equals Z, right, we're assuming that, and this thing here is AZ plus B over CZ plus D. So if I multiply this thing by CZ plus D over CZ plus D, right, then I get Z times CZ plus D. That's exactly the condition that Z be fixed by gamma. And so now these two equations, gamma of 1 is CZ plus D, or sorry, G of 1 is CZ plus D, G of Z is CZ plus D times Z. Right? That means you're C linear. Right? The Z is pulling out just like if it was a complex linear map. And that's exactly what you need to induce a map of the elliptic curve. Right? It's a C linear map of the ambient complex space, and it preserves the lattice. So this tells us that this G induces an automorphism of EZ. And then you can reverse the reasoning and go backwards. I'm not going to give the details. So the automorphism group of EZ is, of course, the group of units in the endomorphism ring. And what do we know about the endomorphism ring? What do you know about the endomorphism ring of an elliptic curve? No one knows anything. The endomorphism ring of any elliptic curve is either Z or an order in an imaginary quadratic field. And so the units of Z are plus and minus 1. That was important in the last lecture. The units of O, what are the units of an imaginary quadratic field? An order. So in one case there's 4, and in one case there's 6, and otherwise it's just C, plus or minus 1. So O star is Z mod 4Z if O is Z adjoin I. And it's Z mod 6Z if O is Z adjoin rho, or rho here is the 6th root of unity, and it's plus or minus 1 otherwise. So if we want to find our point z where we have an interesting stabilizer. Plus or minus 1 counts as not interesting. So one of these two cases. We want to find where our elliptic curve has endomorphism ring z join I or z join rho. And here's how that works. So suppose E is an elliptic curve, and its endomorphism ring is z join I. Well, then E is isomorphic to the elliptic curve E sub I. So just C mod z join I. So there's only one of isomorphism. And here's the proof. So we can write E as C mod a lattice. And this lattice is a z join I module. So lambda is it's torsion free, right? Because it looks like z squared. And it's a z join I module. So what does that imply about it as a module? Y is a principal. That's right. So I prefer to think in 2 steps. So first of all, this is a Dedekind domain, right? And whenever you have a torsion-free module over a Dedekind domain, it's projective. So that says that lambda is projective. And then since the class number is 1, every projective module is free. So the key point is the class number is 1. So because the class number of Q join I is 1, the class group is 0, lambda is actually free. And of course it has rank 1. So it has rank 2 over z. So that means there's just some generator. So lambda is z join I times some element alpha. And that equation, exactly says that lambda is homothetic to the lattice generated by I. And this is actually alpha times the lattice lambda sub I. So these two guys are isomorphic. And the same thing holds in the rho case. So if ND is equal to z adjoin rho, then E is E rho. And the argument's exactly the same. The point is the class number is 1. In general, if you look at things that have CM by a fixed order, the set of isomorphism classes is the class group of that order. Okay, so what we've just said gives us a complete understanding of stabilizers. So let me summarize the situation. So suppose Z is in the upper half plane, not a cusp, like actually the upper half plane. Then one of the following is true. So Z can be in the orbit under gamma 1 of the point I. And this is equivalent to gamma 1, this kind of reduced stabilizer group being Z mod 2Z. Gamma can be in the orbit of rho. This is the same as this stabilizer group being Z mod 3Z. Or Z could be in neither of the orbits. And that's the same thing as saying that the stabilizer is trivial. So up to the action of gamma 1, there's really only 2 points that are a problem, I and rho, in the upper half plane. Are there any questions about this? Well, so we also need to worry about the cusps. And so the stabilizer there is easy to compute. So Z is a cusp, and this guy is cyclic of infinite order. And here's the proof. Well, since all the cusps are conjugated, it suffices to consider any one of them, so we can just work with infinity. So it's easy to see a copy of z inside the stabilizer. I mean, if z plus n is equal to z, right? If n's an integer, because z is infinity. And so this means that this matrix 1 and 1 stabilizes. That's for all n. And then conversely, everything is of this form up to a sign. And the way to see that is, I mean, if we take some element a, b, c, d of gamma 1, so gamma acting on infinity. So remember, gamma is the linear fraction transformation az plus b over cz plus d. So if you let z go to infinity, you just get a over c. And so this is equal to infinity if and only if c is 0. And that means you have this form up to plus or minus. So that's the full stabilizer, in other words. Okay, good. So we understand stabilizers of points for gamma 1, and then this tells us stuff about stabilizers in general, and for subgroups of gamma 1. So suppose that we have some finite index subgroup. So we make a definition. We say that a point in the upper half plane is elliptic for gamma if the stabilizer is non-trivial. And then we say the order of z is the order of that group. So since gamma is a subgroup of gamma 1, this stabilizer group is going to be a subgroup of the stabilizer group for gamma 1. And that's, I mean, that's always either trivial or z mod 2 or z mod 3. So you only get elliptic points of order 2 or 3. And so if z is an elliptic point of order 2, that means that z is in the orbit under gamma 1 of I. And similarly, if it's order 3, then it's in the orbit of rho under gamma 1. The converse isn't true, right? I mean, you could have a point that's in the orbit of gamma 1, but it doesn't necessarily have to have a stabilizer in gamma. Gamma could be too small. But at least you know that everything that does have a stabilizer is in one of these two orbits. And so the only points that with non-trivial stabilizers are these elliptic points and the cusps. And there's the number of gamma orbits of them is finite. The number of gamma 1 orbits is just 3. All right, so using these stabilizers, we can get some information now about what these spaces look like. So suppose that I have gamma inside of gamma prime, which are both finite index in gamma 1. So then you get an induced map on the quotients. So I'll call that F. And let Z be a point on that upper half plane, and let P be its image in X gamma. Then what I want to say is we can compute the ramification index of P along this map F in terms of these stabilizer groups. So it's just the index, like this. Okay, the proof of this is pretty easy. So take an open neighborhood U of Z inside the upper half plane. and choose it so that it's stable by the big stabilizer group, gamma prime z. And you can do that just by adding in the translates of u under this group if they're not already there. So you get this diagram then. U mod gamma z, this maps to x gamma. And then we can do u mod gamma z prime, and this maps to x gamma prime. And of course there maps down. And these horizontal maps are homeomorphic. I mean, they're basically homeomorphisms. They're not surjective, but I guess you'd say local homeomorphism. Right, I mean, if you take a small enough neighborhood of z, if you use a small enough neighborhood of z, then the only points in U that get identified in the quotient are ones that are off by the stabilizer of z. That's some property of these groups in the action, that it's like completely discontinuous. You need a nice enough action for that to be true. It's true in this situation. And so here I just have the same U, and I'm just killing a bigger group here. And so this thing, at least generically, I mean, the number of points in the fiber is going to be the index. Right, so that says that if you move a little bit away from z, the number of points in the fiber is the index, and that's how you compute the ramification index. So this thing here is generically indexed to 1. All right, so that proves that. Are there any questions? All right, so we can put all these pieces together now and prove something cool. Here's the genus formula. So gamma is a subgroup of index D. I'm going to let nu2 be the number of gamma orbits of elliptic points of order 2. Nu3 is the same thing for 3. Nu infinity is the number of cusps, gamma orbits of cusps. And I'll let G be the genus of X gamma. And the formula is that G is 1 plus D over 12 minus nu2 over 4 minus nu3 over 3 minus nu infinity over 2. Okay, and so let's prove this. So that idea, so a good way to compute the genus of a curve is to take a map to P1 and use Riemann-Hurwitz, and that's what we're going to do here. We have a convenient map to P1 because, I mean, the quotient of the upper half plane by gamma 1 is P1. So we have this map F from X gamma to X1, and this thing here is just P1. And so we're going to apply Riemann-Hurwitz. So the Riemann-Hurwitz formula says that if you do 2 minus 2g, where g is the genus here, that's equal to 2 minus 2 times the genus here, which is just 2, because P1 is genus 0, times the degree, d, minus the sum of the ramification indices minus 1. Here the sum is over all points P in X gamma, and EP is the ramification index. All right, so in our case, we know that these ramification indices you can compute by these stabilizer indices. And you only get interesting stabilizers at the cusps and elliptic points. And those, and there's only 3 of them on x1, the images of I, rho, and infinity. So you only get stabilizers in those 3 fibers. So we'll handle each one of those separately. So let me name them. So Q2 is going to be the image of I in x1. Q3 is the image of rho in x1. And Q infinity is the image of infinity in x1. So this sum here, and this is really, you can sum over the points over Q2, and then add back the sum of the points over Q3, plus the sum of the points over Q infinity. And so we're just going to compute each one of those sums separately. All right, so let's do the Q2 one first. So the points above Q2 are the points that are in the gamma 1 orbit of I. Some of them may have stabilizers for gamma, some may not have stabilizers. The ones that do are called the elliptic points, right? And so those things, I mean, since the stabilizer in gamma 1 is Z mod 2Z, the stabilizer in gamma either has to be the full thing or nothing at all. So if you're an elliptic point, then your stabilizer is the full thing, and so the index is 1, which means your ramification index is 1. And if you're a non-elliptic point, then your stabilizer is trivial, and so the ramification index is 2. So the elliptic points over Q2 are unramified, and the non-elliptic points over Q2 all have a ramification index 2. The total number of points, if you count with multiplicities, is the degree. And so from that we can figure out how many points are ramified. Right? So I do the number of unramified points, so that's nu 2. And if I add 2 times the number of ramified points, this is supposed to be d. So this says that the number of ramified points is d minus nu 2 over 2. And so if I look at this sum over f of p equals q2 of ep minus 1, each of the ramified points contributes 1, and each of the unramified points contributes 0. So this is just the number of ramified points, which is that. This is d minus nu 2 over 2. And a very similar computation shows the sum over Q3 is 2 times d minus nu 3 over 3. And over infinity, you can do it the following way. So if you look at the sum of f of p equals q infinity, ep minus 1, we can write this as the sum of f of p equals q infinity, ep minus the sum of f of p equals infinity, q infinity of 1. And this is the number of points in the fiber counted with multiplicity, which is d. And this is the number counted without multiplicity, just the number of cusps, which is what nu infinity is defined to be. So that's the answer there. All right, so if you put these computations together, you have 2 minus 2g is 2d minus each one of these things. So minus d minus nu 2 over 2, minus 2d minus nu 3 over 3, minus d minus nu infinity. And now you just simplify, because it's solve for g. Any questions? So this formula is useful because these numbers d and u's, you can usually just, they're pretty easy to compute. It's usually just in terms of the group theory of gamma. So let me show you a few examples. I think I'll write some exercises for you along these lines. These are good computations to do if you've never done before. So let's suppose that n is prime. And let's consider the case where gamma is gamma 0 n. So in this case, the numbers are as follows. D is n plus 1. That's the degree. The number of cusps is just 2. The number of elliptic points is 1 if n is 2, 2 if n is 1 mod 4, and 0 otherwise. The number of order 3 is 1 if n is 3, 2 if n is 1 mod 3, and 0 otherwise. So this is the kind of computation that's really worth doing if you haven't done it before. Try to figure out these formulas. And so you can plug these in and get the formula for the genus, and if I simplified it correctly, I think it comes out to the following. It's the floor of n over 12 plus a correction factor of minus 1 if n is 1 mod 12, and 1 if n is 11 mod 12. So for instance, the genus is 0 if you look at primes that are less than 13, except for the prime 11 where the genus is 1. And you can see from this that the genus is going to infinity basically linearly in n. So there's only going to be finitely many of these curves of a given genus, at least if we restrict to prime. That's true for composite as well. Another example. The genus of x1n is equal to 0 if and only if n is less than or equal to 12 and n is not equal to 11. Okay, so you can prove that by computing these numbers in general for n and then looking at the formula and seeing this. The significant thing about this is these are exactly the values of n where you can have a n torsion point on an elliptic curve over Q. Right? In Mazur's theorem, these are exactly the values that are allowed. And that's not a coincidence. So when we talk about these moduli problems over Q, we'll be able to explain why that happens. Are there any questions?
What is this?
floor of n over what?
Where are you?
G equals the floor of,
Floor of n over 12.
oh, 12.
Yeah.
Okay.
Okay, well, that's all for today.